Okay, so prove by induction, prove that this expression that we have here is divisible by 5 here. So here we're going to say that we need to show that it's true for n equals to 1 here. So meaning that when we substitute with 1 where there's n here, whatever number we're going to get there, it should be divisible by 5 without leaving a remainder there. So here, so we're going to put a statement here. We need to show that. So we need to show that it's true for n equal to 1. So we have this statement here. We have 9 to the power, where there's n, we substitute with a 1 there, so we have 9 to the power 1 plus 2 minus 4 to the power 1 here. So this will just be equal to 9 to the power 3 minus 4 to the power 1. So this will be, should be 729 minus 4, which will give us 725 here. So now if you look at this 725 here, this is divisible by 5 here. So this 725 is divisible by 5 without leaving a remainder there. Okay, so if it is divisible by 5 without leaving a remainder there, so I'm just going to say therefore it's true for n equal to 1 like this here. So now step number 2, we make an inductive hypothesis. So the inductive hypothesis here, okay, so on the inductive hypothesis we make an assumption that it's true for n equals to k here. So we assume that the statement that it's true for n equal to k like this here. So we need to show that the statement is true for n equals to k there. So now to do this here, since we're making an assumption to say that it's true here, so okay, so since we're making an assumption that it's true there, so we're going to get this expression here where there's n, we substitute the k, then we equate it to 5 multiplied by a variable of our choice. So we can make it x, we can make it m, or n, whichever variable of our choice that we can work with there. So meaning that here we're going to have 9 to the power k plus 2 minus 4 to the power k is equal to, let's say, 5m like this here. So now here, if we have powers that are being added, it means that we had numbers with the same base but just different powers that were being multiplied here. So basically here, this is the same as 9 to the power 2 here multiplied by 9 to the power k equal to, we shift this negative 4 to the power k the other side, so we have 5m plus 4 to the power k like this here. Okay, so now here we make 9 to the power k the subject, so we have our 9 to the power k there being equal to 5m plus 4 to the power k divided by 9 to the power 2 like this here. Okay, let's leave our inductive hypothesis at this stage here. So now we need to show that this is also true for n equals to k plus 1. So here we just say we need to show that this is also true for n equal to k plus 1. So what we're going to do now here is we're going to get the expression the way it is. We write where there's n, we're going to put k plus 1. Then we don't equate it to anything, but instead we just start simplifying it the way it is. So what I'm talking about here is we get our 9 to the power k plus 1 plus 2, 9 to the power k plus 1 plus 2 like this, minus 4 to the power k plus 1 like this. So now if we start simplifying this here, we're simply just going to have 9 to the power k plus 3 minus 4 to the power k plus 1. So if the powers are being added, then the base is the same, just that the powers were different. So meaning that here we're going to have 9 to the power k multiplied by 9 to the power 3 minus 4 multiplied by 4 to the power k like this. Okay, let me just scroll down a bit. Okay, so now where there's 9 to the power k here, remember we had 9 to the power k being equated to something on the inductive hypothesis there. So we're going to do the same thing here. Where there's 9 to the power k, we're going to substitute with this expression that we have here. So meaning that here we're going to have 9 to the power 3, open brackets, 5m plus 4 to the power k divided by 9 to the power 2 here. We close minus 4, and we have our 4 to the power k like this here. Okay, so now after doing that here, you notice that this here will cancel with that one there. We're just going to remain with the 1 there. So meaning that here we have 9 times 5, we're going to have 45m plus 9 multiplied by 4 to the power k, we're going to have 9, 4 to the power k minus 4, 4 to the power k like this here. So now 4 to the power k here, we're going to treat it as a variable, so meaning that if this is a variable here and this is a variable, the sheet there, so meaning that we can either add or subtract the coefficients that we have in front of it. So here, this number is the same as when we say 2x like this. We know that x is a variable here, like this. We can either add or subtract the coefficients here, but we know that we keep the variable the way it is here. So meaning that this can just give us negative 1, so which is just negative x here. So now here, we do the same thing here. 4 to the power k is a variable for this number that we have here. So meaning that this here will just be simply 45m plus 9 minus 4, it will give us 5. Then the variable that we have here is 4 to the power k like this here. Okay, so now here we can just factor out the 5 because it is a number that we have there in the question there. So if we factor out a 5, we're simply going to have 5 open brackets 9m plus 4 to the power k like this here. So now whatever values of m and k that we can put here, we'll still get a number that will be divisible by 5 because we have a 5 that here that will be multiplied by this number here. So if we're able to factor out a 5, it shows that this number here that we have is going to be divisible by 5. So then here we're just going to put a statement there saying therefore this is true for n equals to k plus 1. So if it's true for n equals to k plus 1, then this holds. Under mathematical induction. Okay, so this holds under mathematical induction there.